rule number 3, let's try out this one together with a couple examples. So again, we want to only have positive exponents here. Our first example, we've got 3a squared, and that's all being raised to the third power. Now, when we have any base or any power being raised to another power, we simply multiply those two together. And we have two different terms here that we have to consider. So 3 is being raised to the third power, and a squared is also being raised to the third power. So I'll write that like this. Now we have that this was a 3 to the first power, so the 3 times 1 gets us that 3 to the third. And now we have an a squared to the third power, which is going to give us a to the 2 times 3 power, which will give us a final answer of 3 to the third times a to the sixth. And I'm going to write this one out the long way too, just so we can see what's happening here in another form. So if we have 3, I'll do this in a different color, make it a little more clear. We have 3a squared to the third power. Well, what that means is we're taking everything inside our parentheses here and multiplying it together 3 times. So we'll get 3a squared times 3a squared times 3a squared. Now we can see when we're multiplying this together, this is really just a repeated version of our first exponent rule here, where we're multiplying like bases. So we have 3 to the first powers, which gives us 3, 1 plus 1 plus 1. And that's being multiplied by our 3a squareds. So we'd get a to the 2 plus 2 plus 2, giving us that total of 3 3s and 6 a's. So 3 to the third and a to the sixth. Same final answer, just a different way to consider it. Let's try that again in letter B. This time I'll show you usually how I think of these. I think it's a little quicker to go through. I pretty much just distribute our exponents to each term individually here when we have our parentheses raised to a power. So I'll distribute that 2 to our 6th term, and to our y term, and to our x term here, which would get us 6 squared times y squared times x to the 4th squared. And this is going to result in using our power rule again on that last term. So we have 6 squared y squared x to the 2 times 4th power, which will become x to the 8th power. So that's not so bad so far. We're just distributing in that exponent to each of our terms individually. Let's try out letter C together. So let's bring in that 2 to, well, it'll be easiest here to simplify what's inside our parentheses. That's what we should always be doing when we have anything inside parentheses. Regardless, working with our PEMDAS, we should be focused on our parentheses first before our exponents. So let's do that first. We've got our 3 times our 2, going to give us a 6 here. So 6x squared times x squared, all raised to the 2nd power, which will become 6x to the 2 plus 2 power, and that's being squared, getting us 6x to the 4th power, all being squared. And now let's focus in on our exponent on the outside of the parentheses. We'll bring that into each of our 2 terms here, where we get 6 squared times x to the 4th, and that's being squared, giving us, should be doing my equals here, giving us a final answer of 6 squared times x to the 8th. We're just multiplying our 2 and 4 together. Let's do one last example for this. So again, let's multiply our constant terms first, giving us a 4 out front. Then I'm going to rewrite my variables, again because multiplication is commutative, just so they're right next to each other. So x cubed times x to the negative 1, y to the negative third, and y to the third. Now when we do our power rule, our product rule, our first rule, we can simply just add our exponents together for our like bases here. So we'll get x minus 3, because that's plus negative 1, times y to the negative 3 plus 3. And this will get us 4x squared times y to the 0 power. So we got negative 3 times 3, or negative 3 plus 3, giving us 0 here. And this is actually a pretty unique situation here. We've got y to the 0, and anytime we have a power raised, or a base raised to the 0 power, that's equivalent to 1. So this will reduce even further to 4x squared. And let me show you why that works out. So if you remember our nifty quotient rule, that second one up here, x squared, or x to the a over x to the b, is equal to x a minus b. Well, if we have, I think the easiest way to do this is to show you with a number example. So let's say we have 2 to the third power, and that is being divided by 2 to the third power. Well, we know our quotient rule says this is equivalent to 2 to the 3 minus 3, which is going to equal 2 to the 0. So our quotient rule says this is true. We also know, however, whenever we have any number being divided by itself, that's equivalent to 1. So we also know 2 to the third over 2 to the third is equal to 1, again because any number divided by itself is equivalent to 1. Well, if we say 2 to the third over 2 to the third is equal to 2 to the 0, we're also saying that it's equal to 1, so we've got to conclude that 2 to the 0 is equal to 1. And that will hold true for any real value. So that's why when y to the 0 came up, I simply just said it's equal to 1. And I dropped it from our final answer. Now let's try a couple of word practice problems together. So we've got an equation shown below of 3a to the fourth times a squared, and we want to see that's equivalent to 3a to the something. And we've got to figure out what that something power is. Well, here we can see we're using our product rule, where we have our two like bases being multiplied by together with different exponents. So we know immediately we're going to use our product rule and say 3a to the fourth times a squared is equal to 3a to the 4 plus 2. Then let's see which answer here looks right. The missing value is 6, because 3a to the fourth times 3a squared is equal to 3a to the 4 plus 2. Well, 4 plus 2 is equivalent to 6. So I would agree with that first answer here. We get 3a to the 6th power, giving us a as the correct final answer. We didn't even have to look at B, C, or D. That was nice and easy.